Hello, everyone. I'm Sophia Chen, and today I'm going to take you on a journey through something that contains everything you've ever known, will know, or could possibly know: the universe itself. More specifically, we're going to talk about its shape. I know what you're thinking. The universe has a shape? I thought it was just everything. Well, that's exactly what makes this so fascinating. So let's start with the big revelation. Our universe comes in one of three possible shapes, at least according to our current understanding. These shapes aren't about how galaxies are arranged or where black holes lurk. They're about the underlying geometry of space itself. Imagine you're an ant walking on the surface of different objects. If you're walking on a flat piece of paper, that's one kind of geometry. If you're walking on the surface of a ball, that's another. And if you're walking on something shaped like a saddle or a Pringles chip, that's yet another. The universe is a bit like that, except in more dimensions and without the delicious potato snack flavoring. The three possible geometries of our universe are flat universe or universe with zero curvature, spherical universe or universe with positive curvature, and the last one is hyperbolic universe or universe with negative curvature. Each of these has profound implications for the past and future of everything that exists. No pressure, right? Just the shape of all reality hanging in the balance. Let's start with the flat universe. In this scenario, space has what mathematicians call zero curvature. Parallel lines stay parallel forever, and the interior angles of a triangle always add up to 180 degrees. It's the geometry we all learned in high school, Euclidean geometry. If you could draw an enormous triangle between three distant galaxies in a flat universe, its angles would add up to exactly 180 degrees. That seems intuitive to us because the geometry we experience in our everyday lives approximates flatness. But remember, the apparent flatness of the Earth once seemed intuitive too, until some clever ancient Greeks started noticing ship masts disappearing over the horizon. A flat universe is like a never-ending piece of paper extending infinitely in all directions. It would keep expanding forever, though the expansion would slow down over time due to gravity. However, it would never quite stop or reverse. Think of it like throwing a ball upward at exactly escape velocity. The ball will keep moving away, getting slower and slower, but never actually stopping. That's our flat universe, the cosmic Goldilocks, not too curvy in either direction. Interestingly, all evidence we have so far suggests that our actual universe is remarkably close to flat. We're talking flat with a precision that would make a spirit level jealous, but more on that evidence later. Next, we have the closed or positively curved universe. This is like the surface of a sphere, but in higher dimensions. In this geometry, parallel lines eventually converge, and the angles in a triangle add up to more than 180 degrees. Imagine drawing a triangle on a globe. You could make one with three 90-degree angles, giving you a total of 270 degrees. That's impossible on a flat surface, but perfectly normal on a sphere. A closed universe is finite but unbounded. That's a mind-bender, I know. It means that if you traveled in one direction long enough, you'd eventually return to your starting point, like circumnavigating the Earth. But unlike the Earth, there's no outside to this universe sphere. The surface of the sphere is all there is. In terms of its fate, a closed universe would eventually stop expanding and start contracting under its own gravity, leading to what cosmologists call the Big Crunch, essentially the Big Bang in reverse. Everything would collapse back to a singularity. It's cosmic recycling at its most dramatic. Here's a slightly unsettling thought. If we do live in a closed universe, and you look far enough in one direction with a powerful enough telescope, you might theoretically see the back of your own head. Talk about the ultimate selfie opportunity. Though I should note you'd have to wait billions of years for your light to travel all the way around the universe, by which time you'd probably have different hair anyway. Finally, we have the hyperbolic or negatively curved universe, which is shaped like a mathematical saddle or a Pringles chip. In this geometry, parallel lines diverge and triangles have angles that sum to less than 180 degrees. Hyperbolic geometry is the wild child of the geometrical family. It's so counterintuitive that it wasn't even properly developed until the 19th century, long after Euclidean and spherical geometries were well understood. If you've ever seen those fancy crochet models that look like coral reefs with ruffled edges, those are physical representations of hyperbolic planes. The ruffles aren't decorative, they're necessary to represent the excess space that exists in a negatively curved geometry. A universe with hyperbolic geometry would expand forever, and not just that, its expansion would never even slow down significantly. It's like throwing a ball upward with more than escape velocity. Not only does the ball never come back, but it keeps moving away at a considerable speed forever. In a hyperbolic universe, there's so much space that parallel lines not only stay apart, they actually get further apart the longer they go on. It's like the universe is constantly creating more space between everything. Now that we've met our three cosmic contenders, let's talk about how mathematicians and physicists actually describe and calculate this curvature. The concept of curvature was formalized in the 19th century by mathematical giants like Carl Friedrich Gauss and Bernhard Riemann. Riemann extended Gauss's work on curved two-dimensional surfaces to higher dimensions, creating what we now call Riemannian geometry. This turned out to be exactly what Einstein needed when he was developing general relativity. The fundamental equation that relates to cosmic curvature is the Friedmann equation, developed by Alexander Friedmann in the 1920s. It's derived from Einstein's field equations of general relativity, and it describes how a universe expands or contracts over time. The simplified version looks something like this equation. Okay, I know that looks intimidating, but let's break it down. H is the Hubble parameter, which measures the expansion rate of the universe. A is the scale factor, which tells us how much the universe has expanded. Omega m represents matter density, that's including us. Omega r represents radiation density. Omega k represents the curvature of space, and omega lambda represents dark energy. The curvature term omega k is what we're interested in today. If omega k equals to 0, we have a flat universe. If it's positive, we have a closed universe. And if it's negative, we have an open hyperbolic universe. But here's where it gets interesting. The Friedmann equation tells us that the geometry of the universe is directly tied to its density. There's a critical density that precisely divides the three possible geometries. If the actual density equals the critical density, the universe is flat. If the actual density bigger than the critical density, the universe is closed. And if the actual density less than the critical density, the universe is open. This critical density is approximately 5 hydrogen atoms per cubic meter. That's astonishingly empty, far emptier than even the best vacuum we can create on Earth. Yet, as far as the cosmos is concerned, this is the dividing line between an open and closed fate. To put that in perspective, let me tell you how empty 5 hydrogen atoms per cubic meter is. If you take a volume of space the size of the Earth at the critical density, it would contain the mass of about 3 Mount Everests. The universe is mostly empty space, with matter being incredibly rare, which makes it all the more remarkable that the actual density appears to be so close to this critical value. So that's all very nice in theory, but how do we actually measure the curvature of the entire universe? It's not like we can step outside of it with a cosmic protractor. This is where observational cosmology gets clever. We have several independent methods to measure cosmic curvature, and they've all become increasingly precise over the past few decades. Method number 1, the cosmic microwave background, or CMB. The cosmic microwave background is essentially the afterglow of the Big Bang, the oldest light in the universe. It's radiation that has been traveling through space for about 13.8 billion years, since the time when the universe became transparent about 380,000 years after the Big Bang. The CMB appears to us as a nearly uniform glow of microwave radiation coming from all directions in the sky. But when we look very closely, we see tiny temperature fluctuations, slightly hotter and colder spots that differ by about 1 part in 100,000. These fluctuations form patterns of different sizes. The most prominent pattern is what cosmologists call the first acoustic peak, which represents temperature variations at a specific angular scale. Here's the key insight. The apparent size of this peak depends on the geometry of the universe. Think of it like this. Imagine drawing a circle with a 1-meter radius on different surfaces. On a flat surface, the circumference is exactly 2 meters, about 6.28 meters. On a sphere, positive curvature, the circumference is less than 2 meters. And on a saddle, negative curvature, the circumference is more than 2 meters. Similarly, the same physical size of fluctuations in the early universe appears different to us depending on the cosmic geometry the light traveled through to reach us. Missions like WMAP, Wilkinson Microwave Anisotropy Probe, and Planck have measured these fluctuations with incredible precision. Their results indicate that the universe is flat to within a margin of error of about 0.4%. That's flatter than a pancake, relatively speaking. If the Earth were as flat as the universe appears to be, the tallest mountains would be less than a millimeter high. I once tried to explain this to my nephew, and he asked, "If the universe is flat like a pancake, why don't we fall off the edge?" I had to explain that flat, in this context, doesn't mean flat like a pancake. It means flat like an infinite plane extending in all 3 dimensions. Though honestly, a universe shaped like an actual pancake would be delicious, if impractical. Method number 2, Type 1a supernovae. Another powerful method involves measuring distances to a Type 1a supernovae. These stellar explosions have a nearly uniform intrinsic brightness, making them excellent standard candles for cosmic distance measurements. By observing how the apparent brightness of these supernovae decreases with redshift, which indicates distance, we can map out the expansion history of the universe. The relation between distance and redshift depends on the curvature of space, so this gives us another way to measure it. The discovery of accelerating cosmic expansion using this method earned Saul Perlmutter, Brian P. Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. Their observations not only revealed the presence of dark energy, but also provided constraints on cosmic curvature. The supernova data align with a flat universe model, though with somewhat less precision than the CMB measurements. It's like getting a second opinion from a different doctor that confirms the first diagnosis. Method number 3, baryon acoustic oscillations. This method sounds complicated, but the concept is straightforward. In the early universe, matter and radiation were coupled in a hot plasma. This plasma had sound waves propagating through it, like ripples in a pond. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, these sound waves became frozen in place. As a result, galaxies tend to be separated by a characteristic distance, the length of these primordial sound waves, which is about 500 million light-years today. We can measure this characteristic separation in the distribution of galaxies across the sky. Just like with the CMB, the apparent size of this characteristic scale depends on cosmic geometry. Measurements of BAO from surveys like BOSS, Baryon Oscillation Spectroscopic Survey, provide yet another confirmation that our universe is very nearly flat. It's like having 3 different instruments all playing the same note. If they're in tune with each other, you can be pretty confident you're hearing the right pitch. The story of cosmic curvature is a beautiful example of how pure mathematics, developed for its own sake, can later turn out to be exactly what physicists need to describe reality. Euclidean geometry, the geometry of flat spaces, had been the only game in town for over 2,000 years after Euclid's Elements was written around 300 BCE. Mathematicians had tried to prove Euclid's fifth postulate, the parallel postulate, from his other axioms, but they always failed. In the 19th century, mathematicians like Janos Bolyai, Nikolai Lobachevsky, and Bernhard Riemann took a different approach. Instead of trying to prove the parallel postulate, they asked, what if it isn't true? What kind of geometry would that give us? This led to the development of non-Euclidean geometries, spherical geometry, where the parallel postulate fails because parallel lines converge, and hyperbolic geometry, where it fails because parallel lines diverge. At the time, this was considered pure mathematics with no obvious application to the physical world. Riemann, in his famous 1854 lecture on the hypotheses which lie at the foundations of geometry, suggested that the geometry of physical space might not be Euclidean, but few took this suggestion seriously. Then along came Einstein with his general theory of relativity in 1915. Einstein needed a mathematical framework that could describe gravity as the curvature of spacetime. Riemann's geometry, which had been developed 60 years earlier for purely mathematical reasons, turned out to be exactly what Einstein needed. Einstein's field equations relate the distribution of matter and energy to the curvature of spacetime. In cosmology, we apply these equations to the entire universe, which leads to the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric, the mathematical description of a homogeneous, isotropic universe. Alexander Friedmann, a Russian mathematician and physicist, derived his equations from Einstein's theory in 1922. These equations describe how a universe expands or contracts over time, and they include the curvature parameter we've been discussing. Interestingly, Einstein initially believed in a static universe and even added a cosmological constant to his equations to prevent collapse. When Edwin Hubble discovered in 1929 that the universe is expanding, Einstein called the cosmological constant his greatest blunder. Ironically, with the later discovery of accelerating expansion, something very much like the cosmological constant had to be reintroduced in the form of dark energy. The history of cosmic curvature is full of such twists. Pure mathematics developed for its own sake found application in physics. Theoretical predictions were confirmed by observations decades later. Terms that were introduced, then rejected, then reintroduced. It's a beautiful example of how science progresses, not in a straight line, but in a curve. Perhaps a flat curve, just like our universe?